Right, so this is a short PrairieLearn homeworks video on running/grading assembly code. And I have beginning steps here because I couldn't get all the way through this, so I'm just going to tell you what I've worked on so far, maybe what the next steps you should be. So here's a high-level overview again. We're on number 19, running/grading assembly code. So to initially run assembly code in PrairieLearn, last video I left off on how to get the Docker image set up. If you just want to run any code, so say I've got this hello world assembly file up on the right side, we need to run 3 commands. So inside of the test.py file within PrairieLearn, within the question, you should have 3 of the PrairieLearn API calls in order to run commands on the Docker image that we created last time. So yeah, there's a hello world example that I've been using to make sure this is all working on the right. So these commands are, so the first one is going to change the permissions. So when you're running these commands, they all run out of the grade directory. So if we look at this first command here, this is essentially opening up all the permissions inside of that grade directory recursively. So that I couldn't find another way to do this. There might be a better way, but when you call this self.run command API call, it runs it in a non-privileged user, which can have all sorts of problems when you're trying to execute binaries, which is what we're doing. So first command does that. Second command is creating an object file from our assembly source. So assembly_file.s, that's our source file. The third command is going to create it's going to link the object file to a binary. And that creates the binary. And then the last command there is the test_run. So that's what actually tests it against, I'm sure you've seen it in the other videos, but that tests it for a result. So expected output is hello world there after running the binary. So here we can see the test passes. It runs that, it executes the binary file. The expected output was hello world. The actual output was hello world. So now that we know that works, we can move on to real interactive questions, grading assembly code that isn't just an example of hello world. So our problem here, yeah, as I touched on earlier, our last topic was just making the image. In order to grade student written assembly, we need to actually dump the registers and memory. So an example question might be something like, write this, like say it's some C code that's like A equals 2, B equals 3, store, and then like C equals A plus B, store the value of C in, I don't know, register 2 or something. So students would have to write that code using assembly instructions, and then they would want to store in register 3, but we have to get that register 3 and check it. So I'll go through steps that I've tried to figure out how to do this. Yeah. So first step I tried, and really the only one I kind of got hung up on it, was dumping the registers with GDB. So GDB is the debugging tool used for C compilation mostly, but we can also use it for assembly here. If we go back to the first command here, or the second one, sorry, arm-linux-gnueabi-as, so that makes our object file. We need to add the gen debug flag. So that'll allow us to have debug symbols inside of our binary, which will let GDB read it, essentially. It's sort of the same thing with C, but it's just -G if you've ever used GDB for C. We also need to make a breakpoint at the end of the assembly file. Could be at the beginning too, but as long as you're able to add a breakpoint, you should be able to see all the registers. So like if you add a breakpoint at the end, you can then run it with GDB and then run the GDB commands, info registers, and it'll print all your registers. There's another one for memory, can't remember it off the top of my head, but you can do that as well to see the memory. And then once you have those printed, you can parse the results probably with something like AWK on Linux or similar. And then you can get that back into your Python file and test for expected results. So yeah, dumping the registers with GDB. I tried doing it as well as with GDB multi-arch to maybe fix the problems with it not liking that it's in ARM assembly instead of x86. But I couldn't really get it to work here. If you see on the right, it is printing registers. Those are x86 registers though. And it's all zeros, except for RSP, but that's just a pointer. So, and these aren't even starting from register 8, and I was trying to store a value in register 0, so I don't know how to access, I don't know how to see that register 0. So yeah, the values are not what I'm expecting. I also tried using GDB TUI. You can see on the right there, it actually shows the source assembly code, which was a good sign. But I tried to add a breakpoint, and you can see there, cannot insert breakpoint, can't access memory. I tried doing a bunch of research on why that is. I think it's still because it's expecting x86 assembly and we're using ARM. Not quite sure, but yeah, the breakpoints aren't working. If they did, I think printing the registers in memory would be very simple, but I can't get breakpoints to work. So next steps for you, I think you could potentially see how to get registers through QEMU instead of GDB. That might be easier. I did a little bit of research on actually running QEMU with GDB or through GDB to kind of view those registers like that instead of just running the binary through GDB. So that's an option. Another one is you could keep using GDB, but again, I don't think it likes that it was cross-compiled because it's just expecting a different architecture for some reason. Not exactly sure. Yeah, but that's all I got for this little short video. Hopefully you're able to kind of get past this problem. Good luck.